Welcome to the AbsInt Videocast for the new release 19.4. Today I'm going to present you the latest features for our binary level analyzers, StackAnalyzer, aiT worst-case execution time analyzer, TimeWeaver, TimingProfiler, and the ValueAnalyzer add-on. Let's get started with an overview about our new and simple user management in the AbsInt License Manager program, the ALM. For this, I've opened an ACube for PowerPC client program, and we need first to make sure that we have connected to the license server program. This is done via help license, and here I can connect to my license server, to the ALM, by clicking on this button. It searches a local network. If it finds an ALM that is listening on the port 42424, this is here in my case the ALM running on the local host, and by double clicking on that I can connect to the license server program. What you also see, and this is new, we have two new fields here for user and password combination. This will be the place later to provide user and password data to authenticate against the license program. So we leave it empty by now and connect first to the license server. Then we can open the web front end by clicking on Manage License Server, and the website of the ALM will be opened automatically. There is a new section called Manage Users in the ALM web front end. And when you click there, you can see that you can add new user and password combinations on this section. And well, let's do that right now. I just add a user called user1, and I choose a password, well, 123455. So in real, you should use a better password than this. And the adding of a new user in the LM must always be confirmed by entering the server password. You might remember that the default password, initially at least, was admin. So in my installation that's the case. And when I click on Add User, you see I have a new user added to the AbsInt License Manager who will be allowed to connect to the AbsInt License Manager now. And the rule of thumb is, as soon as you have added at least one user here in the ALM, then all instances of the ACube programs that are connecting to the ALM need to provide a valid user password combination. Okay, so let's add another one to just give you another example. And you see now we have two users who are allowed to talk with the AbsInt License Manager program. Now let's come back to our client program. If I open a new instance of my ACube PowerPC, then you will see immediately that when we now try to connect to our AbsInt License Manager program, we need to provide a valid user password combination, no? As soon as we have entered at least one pair of user password. Okay, so let's come back to Connect License Server, re-choose our ALM on the local host, but this time we are forced to provide a valid user password combination. And now it's successfully connected again. That is our new and simple user management in the ALM. The next topic is the improvements and changes in the graphic user interface and some new AIS annotations. And the very first new feature in this category is a feature that has been wished by many of our customers. Since release 19.4 it's finally available. It's about to refer to individual results of analysis within one analysis project, from within annotations. And this looks like this. Now, from this release on, every analysis will automatically define an AIS variable, an annotation variable called :result underbar, and then the name of the analysis ID, and optionally also the stack type for architectures that have more than one stack analysis. And this variable, this AIS variable, can be referred in user annotations by using the def operator. So you can just refer to it via def :result and then the analysis ID. And here's an example. Assume that we have a big analysis and we would like to exclude the routine proc0 in this main analysis, and instead of annotating a fixed constant stack usage value, we are now referring to some separate analysis where we analyze the routine proc0 separately in a different analysis item. And this can be done by this annotation now. I'd like to give you a demo on that. I've prepared our well-known scenarios example, and especially the 10 millisecond task here. It's a dry stone benchmark program. And I'm going to start this analysis, the stack analysis here. The result looks like this. We have 224 bytes of maximum stack usage, and this is the call graph. And now you could decide that you have, for instance, a too complex analysis, a too complex call graph, and you would follow the divide and conquer approach and analyzing different parts or different parts of this program separately. And for example, I could decide to exclude the subtree, the subgraph of proc0 here from the analysis by introducing a not analyzed annotation from here. Of course, then a not analyzed annotation will be automatically generated, asking me about the stack usage to assume. Up to now, up to this release, we had to provide a constant value here. Well, let's just imagine we have 0 stack usage, which is of course wrong, and assume that the routine obeys the calling convention. So if you rerun the analysis, then you will see what happens. Well, the analysis of course stops here after or at the call of proc0, and the result will be cutted down to 32. Now let's introduce a separate analysis for proc0. We can do that from the graph here as well. Create analysis. Say we would like to create a new analysis, stack analysis for the entry point proc0, and we call it, well, the analysis ID proc0. It takes the placeholder and instantiated it with the starting point. So now we have a new separate analysis called proc0, and we can run that, of course, individually. Result is 192. So we should better here correct our annotation to be safe here to 192. But what happens if somebody later changes the code of proc0 and the stack usage will be increased? The user would have to think about to also adapt the annotation here. This is where always a source of problem or risk when you have here constant values. Now, as I said, every analysis generates, when a result was computed, automatically an AIS variable called result and then proc0, in this case a suffix of the stack analysis type, in this case the system stack. And here's the resulting value. You remember it was 192. And well, then let's now, instead of annotating the constant, let's use this variable. Okay. What we also need to do is, because if I now restart the analysis, you will see the effect. There will be a warning or an error that you have an unknown define of result proc0 system. Because if you just individually analyze this 10 millisecond task where you refer to a variable that has been defined in a different analysis item, this information will not be transported automatically. What you have to do as well is to make your main analysis depending on the proc0 analysis. And this is done by clicking here in the dependencies to the dependent analysis. And now, if I redo the analysis, you will see it will first ask me if it can reuse the results of the proc0 analysis. If I click to no, it will reperform the proc0 in order to really be updated. And well, as you can see, if I reload the graph, now it takes automatically the result from the sub-analysis of proc0 as the stack usage for the not analyzed routine in my main task. This is the new feature of referring to analysis results in separate analysis items. The next two features, the full project search and the DWARF debug info lookup for arbitrary addresses in any of the aiCube's text editor windows, I'm going to directly present in the tool right now. For this, I've opened the scenarios project again, this time with a lot more analysis items in it. And I've prepared already the analysis results. And now I can use the new feature which is called Global Project Search. And this is can be found here below. If you click on that search button, you can search and find over the entire project data, and of course also all the produced output data, also in especially the temporary output data. So let's for example search to some handler variable. If I provide here the name handler, then as I said, it scans every output file, even the temporary intermediate files. Here's the report text file of some analysis, and the analysis ID is put here in the brackets if it's a local output file. And you see whenever handler appears, the line will be referred, and by double clicking on that you jump directly into that file at this location. But also these produced intermediate files will be scanned, automatically generated dependency files, or where is it? Here also resulting graph files will be scanned, so the graph view. If I click here on that line, then it will automatically jump to the place where our user error handler here is called. So it's really an entire global project search. The last category here are the messages for each analysis. So whenever this symbol handler, user error handler, occurs also in the message, this will also be listed here. If I double click on it, you will jump immediately into that message line. To give you an example on the feature of the DWARF info lookup from for arbitrary addresses from within text windows in aiCube, let me just reopen the results of our full project search, global project search, and remember we have searched for the handler variable, and we found some information here in the report file. Let's just double click on that again, and here are a lot of addresses in our text window here, and for instance we could now say, well, we would like to find out more information on this message handler table, which is linked to this address. And if I click here with the right mouse click, I have a new context menu entry here to find this selected address in the DWARF debug info. And if I click on that, I'm automatically switching to the DWARF debug view, highlighting already the searched symbol, or the symbol for the searched address. And if I unfold it here, I get more information about the type structure and for instance sizes. Alright, this concludes the new features in the graphical user interface. Let's now come to the analysis-specific improvements. In addition to many internal changes to the TimeWeaver analysis engine that improve the analysis efficiency and performance in general, I'd like to emphasize in this presentation to a new option that allows to process only complete trace files, or trace snippets basically, and revised start point selection dialog that will filter the starting points with valid entry points extracted from the trace file. I'd like to show you that directly in the tool now. I've opened our scenarios example again, and I'd like to have a closer look to the 10 millisecond task here. As you can see, our analysis entry point is, well, the function called task 10 millisecond try, and in the TimeWeaver hybrid WCAT analyzer, you know, we not just only need the executable to analyze, but also instruction level traces for extracting the basic instruction level timings. And here we provide a Nexus trace file called scenarios.aq.txt. If I now run the analysis, then we can directly go to the last step, the reporting. So worst case execution time estimate of 1.772 millisecond was determined. If I go to the reporting, there's a small trace statistics, and you see the number of trace snippets that have been extracted from our trace file. A trace snippet is basically defined by reflecting one execution path in the real execution from the entry point, the defined entry point, to some endpoint. And in the default case, we really also process trace snippets that start at our entry point, but will never reach one of the endpoints of our decoded task. If you go to the new option under Setup, Timing Analysis, TimeWeaver, Process Complete Traces Only, then this analysis will be restricted to only extract those trace snippets that reflect a complete path execution from the entry point to any of the endpoints of the decoded task. And those incomplete or partial trace snippets will be filtered out. You can see the importance of the next feature when we want to create a new TimeWeaver analysis item. So let's do that by clicking on Create TimeWeaver. And the very first step is usually to provide an input trace file. In our case, it's a Lauterbach Nexus file, and I've prepared it here. It's our scenarios.txt file. And then the next step is usually to provide the analysis entry point. Okay, and for that, we click as user here typically on this pipette symbol, and all symbols from the symbol table of the executable will now be extracted and listed here. So now it was up to the user to select an entry point, which is interesting, interesting to compute a worst case execution time estimate for. But the user had to know that this entry point also comes with a trace event in the input trace data, because this is an important requirement. Whatever you select as an entry point, so I take the func1 here as an entry point, it must be ensured that there is also a trace event for this function in the provided input trace file. So in my case, as you can imagine, we got a problem here, because func1 we don't have trace event 4 in our input file. And the consequence is that the TimeWeaver cannot extract any trace snippet, and of course also not compute any WCT for that. So with this release, we have now introduced to filter this symbol table list only by those, to show only those entries for which we really have a trace input file in the input trace. And as you can see, the list will drastically be reduced in this example, allowing us just to start at our task level entries. So if we go there, then the TimeWeaver can extract timing information from it. All right. The last topic of today's release presentation is specific to our ValueAnalyzer add-on. I will basically present 2 strategies on how to support the user to find out information for resolving function pointer calls or computed calls in the binary analysis. And the first thing is the value analysis all, which is lightweight value analysis on the supergraph consisting of all functions found in the binary. And the next one is an improved or advanced reporting feature for which will list function pointers that have been found in allocated sections. I'd like to give you an example on that in the tool. I have prepared a stack analysis for the 1 millisecond task in this example here. And if I run the analysis, basically interactively by clicking on this play button with the dot, I see 2 unresolved computed calls, so 4 warnings. For each we have duplicated warnings, one in the 1 millisecond task entry function and one in the routine called OSR hook. So let's have a closer look to this location here by clicking right mouse click, showing call graph. We jump to the place in the call graph visualization, and we see that we are branch and linking here over the control register. And now I would like to find out a bit more sorry, what could be the content of this control register. We see here that the content of R0 is put into or stored into the control register. R0 was loaded from here, which is again loaded indirectly from R9. And if we come to that place here, we see that R9 is constructed or is extracted from this memory cell. If I do a right mouse click now, this is already one feature of the ValueAnalyzer add-on. It's the so-called interactive value analysis visualization. If I click there, I see that we are reading from some address here, F0004020, and this basically corresponds to a global variable called registered message handlers. And this registered message handlers variable is located in the .sbss section, which does not come with some constant value, of course, and which means that it is initialized during execution of the application. And this is now an example where we could use our new ValueAnalyzer all, and let's for now copy that address here and generate a new value analysis item in the analyzer overview. You can click here on value analyzer, and with this release, it's now able to not only start a value analysis from one defined entry function. You can also select here all functions or all code labels. Let me, for this example, choose the all functions category, and you see then the selector here is grayed out. That means we will now start here a value analysis over all functions. Means we will build a supergraph consisting of all functions that we extract from the binary. So, and we can also do that interactively. You will see what now happens. We will get a lot of warnings and maybe also some errors, but we can ignore that by now. What is important is we can open now a graph here, and we got a list on the left side with overviews over all functions and with the number of call sites and number of instructions in it. You can double click on it and you see the function on the right side. You can open it. But what is even more important or interesting feature is that you can now do a full search in the supergraph. So with Control F, I can now search for, of course, symbols or function names, but also to data addresses that are written or read from. And if we come back to our result before, it would be interesting to know if we can find a location in the entire application execution where this register message handlers variable was initialized. Okay, so for this we are now searching in our supergraph for program locations where this address is written. So let me put our address here and set the filter to memory writes, basically memory writes data. And well, we find, of course, some locations where we have writes to an unknown address range, but luckily we will also find a location where this memory cell was written in a very precise way. And if I double click on that, I can jump to the place and I directly see, oh, this is happening in the init task function. And since I've started the value analyzer all interactively, I can also do a right mouse click here and click on show value analysis, and I directly also see which value has been written to this register message handlers variable. And now that I have found out the place where this variable has been initialized, I could now go here, say, well, I'd like to do a separate analysis for just this function, separate value analysis. And in this separate value analysis, I could, for instance, define an AIS file. This is another feature of the ValueAnalyzer add-on where I would like to collect the initialization for my register message handler variable. So if I do that, put it here, I have now a separate analysis. I found out with the value analysis all where it is initialized with a meaningful value. And well, now I can connect this concrete initialization analysis with my 1 millisecond task analysis by introducing a dependency. I can say here, I'm depending now on my init task function. And if I redo the analysis, you will see that at least the first computed call has been resolved now correctly with extracting function pointer targets out of message handler table, because if I go back here to the place where it was written, this address here, the content of this global variable corresponds to the start address of our message handler table, which contains constant function pointer targets. Okay, and as you can see, they have been now resolved completely automatically by using this initialization analysis. And we found out the helpful information by using an entire global value analysis. For the demo on the second new feature in the value analysis add-on, assume for now that we have a callback function pointer variable, which is usually assigned directly with function targets, or function targets, and assume further that we have found out with the help of the value analyzer all that I've shown you before, or by source code inspection, that this callback variable is set to some function handle progress message somewhere in the code, in the application. And if we rerun now the analysis, taking this annotation into account, you will see the effect. Well, now instead of following all potential message handler functions, we of course only consider the handle progress message function for taking the path. This is potentially dangerous, that we have not seen all potential callback target functions. With a new feature, we can now, when we have found such a function assignment, we can now copy the name and go back to our report file, which is found here, and we can search for function pointers. And there's a new section in the report file, the value analysis part of the report file, that lists all function pointers that have been found in allocated section. And if we search now for our handle progress message function, we see it directly here. This was found in an allocated section, namely in a read-only data section, and as a part of this message handler table that we have found before. So this could give us a hint that we should not only consider the handle progress message function as the one and only target of the function pointer call. Maybe it would be a better idea to extract all the allocated data here directly from the message handler table. And we can do that by jumping to the DWARF debug info. Do a right mouse click here on this handler component, say copy calls annotation to clipboard, and go back to our AIS file and paste it here. You see it will directly give us the expression here that we can take, and we just cut it here, put it here, remove that, and we also, since I know that already, we need to skip some null pointers because the table not only comes with valid function pointer tables targets, but also contains a null pointer. And that's it. And if we redo the analysis now again, then you see that this time we are extracting again all message handler functions, so we don't miss the potential worst case function. All right, so this concludes the section about the value analyzer add-on. It also concludes the entire presentation of all new features in the release 19.4. Hope that you like the changes. Of course, there are many more, especially in the internal engines of the analyzer, making them more performant in general. If you want to have a closer look to all release notes for this release, please be referred to our website here. And of course, if you have some questions, please feel free to contact us via the email support@absint.com. Thank you very much for your interest. Take care. Bye-bye.